Hello, this is Oliver from Purdue. I'm going to present reachability types, which is joint work with Yuan, Guanan, Luke, Xiang, and Yark. The context of this work is ownership type systems, such as in Rust. And in Rust, we have the shared XOR mutable principle, which basically says that programmers can choose between mutability, but then they have to ensure unique access to state, or sharing, but then it has to be read-only, and there's no middle ground. And this inhibits programming with higher order functions, as I illustrate with this counter example. Here's a counter in Scala that encapsulates a piece of mutable state into two closures that are sharing the state. You cannot create this example directly in Rust without violating the typing discipline. And you have to punch a hole into the type system by using dynamic reference counting that sidesteps the lifetime tracking in Rust. And we are asking ourselves whether we can make this better. And that led to the observation that prevailing ownership and borrowing models follow a specific design pattern, not only Rust, but also other works, which is that they enforce some global invariants, such as uniqueness and linearity, which is permeating their design. And then they layer on top additional mechanisms to give some local relaxation, such as borrowing, or even unsafe features, as in the previous example. We are flipping this on its head, and we don't impose any global invariants. Instead, we are opting for layering additional mechanisms on top of our language and enforce local invariants using some mechanisms. And we use separation and reachability at the type level. Separation comes from separation logic, and so you can think of this work about as rethinking ownership in terms of separation logic. Separation logic has been used already for Rust and giving it a formal semantics. And we are taking this a step further, and we ask the question, what happens if we expose separation overlap all the way to the user-facing types? And we get a very interesting and unique point in this design space for ownership style systems, which leads to our first contribution, which is reachability types in the lambda star calculus. The lambda star calculus assigns types and sets of alias variables, which we call reachability qualifiers, to expressions. In this example, we are allocating a fresh reference, and this reference receives an empty set, meaning it has no sharing with its environment. When we introduce a binding, then the bindings variable is added into the reachability set. Of course, you also have base types in the language, such as integers, but they are not tracked for aliasing. And so we are assigning this bottom qualifier, which means don't track. When we now introduce aliasing, such as assigning this x to y, then we include all the known aliases at this point in the program. In this case, y aliases itself, and it also aliases x. And of course, we have the usual operations, such as dereference and assignment on mutable references. The general takeaway here is that we have a type system that assigns these qualifiers, which can be either bottom or finite sets of variables. And this is otherwise just an ordinary simply typed lambda calculus with subtyping and mutable state and recursion. And despite its simplicity, it's remarkably expressive, as we're going to see. So what about functions, which are kind of the bread and butter for higher order programming? And functions are tracking free variables in their qualifiers. And we are also trying to ensure that there is no unwanted interference with functions and their arguments. So we are using some kind of separation mechanism. Consider this example where we have these two references, C1 and C2, and this addref function that adds a reference to C1. And addref closes over C1 in its environment. So this is the type, and it reflects this fact. So first of all, we note that the function qualifier includes the free variable C1. But we also note that the domain in the function is annotated with the empty set. And this means that we can only pass arguments that do not have anything in common with what the function reaches. In this case, it's C1. Concretely, that means we can call addref with C2, but we cannot call this with C1. This is blocked because of the separation requirement. And this is a useful way to control separation and prohibit unwanted aliasing in higher order functions, which is kind of essential for programming the functions. But if this full separation requirement is too strict, then we can relax this a little bit and allow some degrees of overlap by changing the annotation in the function domain. For example, this version of addref can be called with C1 without problems. And here, for comparison, we can see the type, and we can see that the qualifier in the domain has changed to C1. Now, the next question is, of course, how can we handle escaping closures and continue tracking their variables when they move across scope? Let us look at these concrete examples. First of all, we have this example that's inside of the scope, which I denote with curly braces, returns a function that allocates a fresh reference. And inside the scope, we have the purple type, which says the function has no free variables, and it returns a fresh reference as indicated by these empty sets in the qualifiers. And outside of the scope, this is exactly the same type. It gets more interesting if we add a local binding, such as this Y reference inside of the scope, and then we close over it. Inside, we can see that this is showing up in the free variable, so it's going to be part of the qualifier. But outside, it's not visible anymore, and then we just delete it. And this correctly conveys the intuition that for outside scopes, there is no observable sharing. But what should we do if we change the example slightly and return directly the reference? Because then the Y will also appear in the codomain of the function type. What are we supposed to do now? It is certainly wrong to do naive deletion of the Y, because in this case, we would obtain the same type as the first example, but it behaves differently. In the last example, we return one and the same reference, whereas the first example always returns a fresh reference. So in order to fix this, we are introducing the concept of function self-qualifiers, which is the ability of function types to refer to themselves, which is this F annotation here. And we can use subtyping to abstract over the occurrence of Y using this function self-type. And then we can leave the scope and correctly delete the closed over Y. And this is then the final type. And it is a different one from the freshness example. And the intuition is that these function self-qualifiers are somewhat like abstract types in dot and Scala. And the presence of these qualifiers indicates some qualifier escapes, but it's not clear which one. It's kind of like an existential statement or existential qualifier. But we are using subtyping to make using these convenient, because everything is automatically converted as needed and there is no user interaction required. Finally, we also have forms of lightweight polymorphism enabled by dependent types. So here's an example that takes a reference and returns it after incrementing it. And evidently, the qualifier of the results is dependent on the input, which is what makes it a dependent type. And this allows us to encode polymorphism without having the baggage of explicit quantifiers. So, for example, we can call this inc with these different arguments, and the way the input varies is reflected in the result type accordingly. For more details, I refer you to the paper, and there you can also find the full formal system. Now, the system I showed you also exhibits a type soundness, which has a fairly standard arguments. There's some changes of note to the preservation formulation. Here we have to take care of the qualifier. The qualifier is not exactly preserved. The qualifier may increase by allowing fresh allocations only, but that's harmless. However, we get a useful corollary out of preservation, which is called preservation of separation, asserting that we can correctly discern separation and overlapping. It basically says that what is separate stays separate after reduction. And we can just take two well-typed terms which are disjoint, and we can interleave them arbitrarily, and they will remain disjoint. So this is kind of our correctness criterion for what we're doing. There's a caveat, however. We have to limit references to be shallow and forbid nested references, because they can subvert the type system. But later on, we will see a solution how to bring them back into the system. With this basic system in place, we can encode a number of interesting higher order function examples, such as non-escaping values a la Osvald and others from 2016, and effects as capabilities models. For example, here's a try combinator that passes throw capabilities. And we can ensure that these capabilities cannot be accidentally closed over by restricting the return type using this empty qualifier, for example. So here's a usage example, and we can see that it is impossible to return something that closes over this throw capability. And in principle, this scales also to lightweight effect polymorphism and algebraic effect handlers a la Brachthäuser and collaborators. So this is quite impressive that we can already discern this in this basic system, but it's not satisfactory because we cannot, for example, enforce and see consumption behavior such as linearity, which is useful for these capability systems. So for these cases, it makes lots of sense to also add a proper effect system. We can also have non-interference, which I quickly will go over. We can detect if two threads are overlapping or not, and they can then be run safely. Notably, we have here this last example, which is a type error, but it actually is safe because it's just read-only. And this is something we cannot discern with reachability types alone, and this requires, again, an effect system for more finer-grained distinction. And that leads us to our next contribution, reachability and effects. And it makes lots of sense to assign effects to reachability sets, and it gives you a very precise effect system at the granularity of individual variables. And we just have to assign a specific class of usage effects to sets that lifts the system or alleviates the system to a version that is as expressive as these ownership disciplines, which is very interesting. So for example, here are flow-insensitive effects by reading and writing, and they can make the previously unsafe invocation of parallel combinator safe. And we can just look at assigning usage effects to the sets, and we can see here and compare the common overlap of these threads. For example, the overlapped variables are only red, and we can use an effect join to determine that this is safe. But the real killer feature, pun intended, are flow-sensitive kill effects that selectively disable control flow paths. And this is the key to enable linearity and ownership transfer and other phenomena. For example, we have here self-killing functions that, in combination with our self-qualifiers, can enforce that a function can be called at most once, which is pretty useful for use once capabilities or linear one-shot continuations, for example. And finally, using kill effects, we can also recover again nested references using a form of move semantics and ownership transfer. So we can enrich the language with this move operation, also a swap operation. And then we can ensure that nested references always have a unique owner. This is one of many possibilities, of course, and this is a rather simple and effective one. Furthermore, we have interesting case studies, and I encourage you to look into the paper, such as control operators and a whole spectrum of different ones using the features I showed you, algebraic effects and handlers, of course, and concurrency combinators. And finally, the formal foundation for our effect system is the effect quantale framework by Colin Gordon, which can be instantiated, for example, to this kind of structure where we have read, write, and kill effects and sequential composition and join operator. And we are enriching this theory with our own store-sensitive effect quantales, which are essentially lifting an existing effect quantale to reachability sets. Okay, to summarize, our contributions are reachability types, which enable ownership style reasoning for impure higher order functional programs. Notably, we have no global heap invariance. We are statically safe, and we have lightweight types and idiomatic code. We don't enforce any global invariance, which is pretty remarkable. And we have reachability and effect systems based on effect quantales. And all we need to achieve a similar level of expressiveness as existing ownership and borrowing disciplines is having these flow-sensitive kill effects. And finally, please also check out our artifacts consisting of a prototype and a cog mechanization of the base system. Thank you for watching.